All right, hey there everyone, welcome back. We're going to continue our lessons on waves. Today we are talking about two particular phenomena that relate to waves, so it should be pretty short and sweet. We're talking about the Doppler effect, and we're talking about something called beats. So for the Doppler effect, imagine that we had like a little water bug. So we got a happy little water bug, and he's so happy because he just keeps bouncing up and down on the surface of the water. So you could imagine that as this bug bounces up and down on the surface of the water, he's making these little ripples. And those ripples are going to travel away from him in these kind of concentric circles. And so since the waves travel away at the same speed, the separation between them here, the wavelength, would be the same regardless of where you are around the little water bug. Now, imagine this little happy water bug has somewhere to go. So now, as they jump up and down, they're also kind of like zooming across the surface of the water. So maybe they got somewhere to be, so they're traveling this way with a little velocity. Now, what would the shape of the ripples look like? Well, you can imagine that as they make a ripple, they kind of travel towards the wave fronts. They make a wave, but then they travel towards it. And so these circles aren't going to be quite so concentric anymore. They're going to be kind of piled up in front of the water bug and then spread out behind the water bug. And so I notice a very different wavelength in front compared to the wavelength in behind. So there'd be a smaller wavelength in front and a large wavelength behind. Now, the speed of the wave hasn't changed because these are still traveling through the same medium. So what that means then is in front of the water bug, if it has a small wavelength, it would have a high frequency. And if it has a large wavelength, then it would have a low frequency. So you would have experienced this, I'm sure, if you were to ever have a car drive by you, and especially one that was maybe had some sirens like this ambulance here. So you can imagine as the ambulance approaches this observer, the waves in front of the ambulance are kind of packed together, and so you can see that the observer is kind of blinking every time they hear one of those sound waves. Well, once the ambulance goes past, as the ambulance is traveling away from the observer, well, now all of a sudden the waves travel to that observer at a lower frequency. And so you would actually hear this difference. If you had an ambulance approaching you, as the ambulance comes towards you, you're going to notice that that siren is going to sound higher pitch. And then once it passes you, it's almost like it changes key, and all of a sudden the pitch is going to drop to be lower. Now, it's worth noting that we talked about this as being the object moving towards the observer, but of course this would be the same. So if you could imagine, for example, that if I had my observer was the one that was moving. So maybe this little person here, instead of standing around, they're on a skateboard and they're zooming towards a stationary ambulance. Well then, yeah, in that case, they're going to be approaching the source of the sound, and they're going to hear higher frequency sounds as they approach. And then once they go past, they're going to hear the lower frequency sounds, because all motion is relative. So one really cool application of this Doppler shift is cosmological. So you may have heard that we live in an expanding universe, and that's like a really big claim, which kind of seems like, okay, cool, but how could we possibly know that? Well, one thing we notice is when we look around in the night sky and take observations about the galaxies that surround us, and there are many, many, many galaxies surrounding us, we notice something about them. The light that they emit is not quite what we would expect it. When we look at galaxies, we notice that their spectra, which is the colors of the light, are shifted towards the red end of the spectrum. Now, we're going to talk more about light in an upcoming video, but for now, if you know that light is composed of many wavelengths, including the Roy G. Biv of all the colors, red is a longer wavelength. So this Doppler shift happens to the electromagnetic radiation as it's shifted to a longer wavelength. Well, if it's shifted to a longer wavelength, well, then that must be because the galaxy is moving away from us. Or, if you want, we're moving away from the galaxy, and both are true, depending on your perspective. But what's really interesting is that when we look at all of the galaxies around us, virtually all of them seem to be red shifted. The light that they emit is actually shifted to a longer wavelength. And even more interestingly, the further away the galaxy is, the greater this shift is. So the furthest galaxies experience the greatest redshift, which means they're moving away from us the fastest. So the only logical conclusion is, if everything's moving away from us, and the further away you are, the faster you're moving, then all the galaxies are moving away, and therefore our universe must be expanding, which is a pretty cool thing to learn just by looking at the colors of light that's being emitted from those galaxies. Okay, so the second phenomenon that we're going to talk about is something called beats. Now beats, you'll probably notice this as well, and you definitely would have noticed this if you play any kind of musical instrument, especially when it comes time to tune that instrument. If I have two waves that have very similar frequencies but not quite exactly the same, then they create something called a beat pattern. Okay, and so beats are a result of repeating interference. So it's a repeating pattern of constructive and destructive interference that occurs at regular intervals. And it happens because the two waves are close but not exactly the same. So let's take a look at what that looks like. Okay, so imagine I've got one waveform here. You can see this red wave has a frequency of 500 hertz and the blue wave has a frequency of 550 hertz. If I were to play those at the exact same time, the resulting pattern would look like this. Initially they add up in such a way to create constructive interference, but then eventually you can see that they're out of sync with each other and they perfectly cancel each other out. But then that doesn't happen for very long because immediately afterwards they start to get closer to back in sync and eventually they'll be perfectly in sync and so they'll have constructive interference and so on. And so this pattern continues. And what this means is, and again, you would have noticed this if you've ever tried to tune, say, a guitar or something like that, when two notes are very, very close, you can hear a wavering, almost like a wobble sound. What you're hearing is the frequency of the beats themselves. So you can imagine now what's going to happen here to this beat pattern if, imagine my waves are closer together. So right now you can see that they're off by about 50 hertz, which is close, but not that close. What if they're only off by 25 hertz? So let's take this first wave and make it 525 hertz. Now you can see here when I run this, you can see the pattern or the frequency of the beat has gotten smaller, right? You see that the wavelength of the beat pattern overall got larger, which means the frequency has gotten smaller. So the beats are happening less frequently, and this is going to happen as I continue to get closer and closer. So if I reset this and imagine I make this 400 or 540 and I make this go, this is going to take a long time for the pattern to get out of sync and then a long time to get back in sync. And if I go the other way and maybe I make this 450 and I run this, you can see that that's going to have a very high frequency beat pattern. So the frequency of the beat pattern itself really just has to do with the difference in the two frequencies of the waves that are interacting. So what we say is the frequency of the beat, F beat, is equal to the absolute value of F1 minus F2. And F1 and F2 are just whichever waves you want to talk about. It doesn't matter because we're going to take the absolute value and so you subtract one from the other. Essentially it's just the difference. So a student's trying to tune their trumpet to a middle A, which is 440 hertz, and they notice a beat pattern form with a frequency of 12 hertz. What is the frequency of the sound wave they are playing? Okay, well I know that F beat is going to equal F1 minus F2. Now intuitively you might just be able to solve this without using the formula, but we'll do it just to prove a point. If I solve this for F1, which is to say I just drop the absolute value signs and just treat them like a bracket, so F1 minus F2. And so if I solve for F1, F1 is going to equal the frequency of the beat plus the frequency of the second wave, which in this case is going to be 12 hertz plus 440 hertz is going to equal 452 hertz, which is correct, but it's not the only possible correct answer. Because when I've got an absolute value, I need to take both the positive and negative cases. Or just intuitively, you might recognize that 452 is one possibility. The other note could be 12 hertz too high, or of course, it could be 12 hertz too low. So the other possible answer is 428 hertz. And so I don't know which one of those is the correct answer, but it's certainly one of them. All right, that's it for the Doppler effect and beats.